Good morning, everybody. In this chapter, I'm going to go through thermochemistry discussion and thermochemistry discussion. What we do most of the time, we are trying to figure how much energy was exchanged during the process of transferring reactant to products. And through that one, you want to figure that whether you have to apply heat to the reaction to move the reactants to product, or you have to cool the system to make it more efficient. Sometimes in order to get higher efficiency or higher yield, instead of heating the system, you have to you have to cool it or put it in, for example, ice bath, and then you see the efficiency or the yield, it can go close to 100%. And in order actually to go through thermochemistry, we need to have kind of introduction about thermochemistry. And I start with this, that when we talk about energy, total energy, we say the total energy, we can break it down to two parts. The kinetic energy plus the potential energy. And because we are talking about energy, unit for energy, it will be either kilojoule or joule. And 1 kilojoule is equal to 1,000 joule. And I go with this. First part, let's call it here 1, call that one 2. For 1, we go with kinetic energy is the energy that is subject to motion. Okay, subject to motion of object. So that means we need to have velocity bigger than 0. So I'm not talking about volume. V in this case is velocity. Okay. So velocity must be something higher than 0. We say kinetic energy is subject to velocity or movement of object. The formula for it, we go with E equal to half of mass multiply square of velocity. Unit for mass, we go with kilogram, and velocity is meter over second. So the unit for energy is going to be kilogram multiply meter over second, and you square this one, we will get a kilogram to M2 divided by S2. We call this one joule. So now we know the meaning of joule. Joule is equal to kilogram multiplied square of meter over square of second. We have a thermal energy that we say thermal energy is another type of the kinetic energy. Thermal energy is associated with the temperature. Okay, with the temperature. If temperature goes up, then thermal energy is going to go up. Example, this is here. This marker that I'm using is solid right now. The movement of objects or molecules in it really slow. And to that level that we see the shape, like we see it as like one kind of linear or one rod of marker. Okay. If I give it heat, if I give this object heat, molecules or atoms inside this marker start to move faster. When they move faster, they can get a bit far from each other. And when they get far from each other, and we see that we slowly we start to losing the shape of this marker, and it turns to liquid. So by increasing temperature and increased movement of atoms or molecules inside this marker, and the shape or let's say the state of the compound from solid turn to liquid. So anytime you go from solid to liquid to gas, we are increasing thermal energy, or simply we are increasing kinetic energy in this case. So I can say kinetic energy to the right side is going up. Okay, from solid to gas, we are giving heat or energy to the system. So I'm going to say the movement is going to be higher in the system. It will have higher thermal energy or kinetic energy. Next thing that we're going to go through it is going to be number 2. Number 2 says the potential energy. So potential energy is the energy that's subject to position of object. So here, potential energy is the energy that subject to position and composition. When we say potential energy is subject to position, we can write it as here, or show it by this formula mgh. M is mass, and we go with unit of kilogram. G is the gravity acceleration, 9.80. Unit is meter over second, square of second. Next one is the H, is the height, and height is equal to, it has unit of meter. So a unit for potential energy is going to be kilogram for mass multiply meter over square of second multiply H, which is meter. We get kilogram multiply M2 divided by S2, and this is joule. Okay. So again, we got joule, and because we got joule, we can add it to the kinetic energy. I said the potential energy is subject to position. If you change H, then the potential energy is going to go up or down. And here is the example. Assume H in this case is equal to 2 meters. And you have object here, and you push the object, and the object it will move down. And compare it with this case. That again, we have the object here, but this time H is equal to 6 meters. And I want to compare them. I want to compare the potential energies. Let's talk about the starting point. What do we have in the starting point? In starting point, velocity is equal to 0. So you say velocity is equal to 0. There is no movement. That means kinetic energy is going to be equal to 0. Okay. So whatever you have as an energy is going to be absolutely just potential energy. And the potential energy is going to be equal to mgh. What's the h? H in this case 2 meter. So you go potential energy is equal to 2 mg. Okay, 2 mg. That's the maximum potential energy that you can have. So I'm going to say here we have the max for potential energy. Okay. When you start, when you start moving, or when you push the object and the object start moving, then we are taking some energy from the potential, we transfer it to the kinetic energy. And I'm going to show you that one. Right before we hit the surface, velocity is max. Okay, velocity is max. That means you have the maximum kinetic energy. This one is going to be max. And the potential energy is going to be minimum. Okay. Compared with this one, we will have the same story. So here we're going to say potential energy is max, kinetic energy is 0, equal to 0, and here potential energy is equal to, it's not correct to say 0 because it still is higher than the surface, but it's close to 0. Okay, close to 0. So I'm going to say potential energy is minimum and the kinetic energy is max. Well, what's the potential energy in this case? Potential energy is going to be mgh. H is equal to 6. We get 6 gh. So compare it with this one. Okay, 2gh, 2mg versus 6. My bad. This one should be m. Okay. So 2gm versus 6gm. By changing h, we increase the potential energy. Okay. So you have an object that somewhere here, and you let it go. Let's say this is h. H is equal to 6 meter. Here, I'm going to say number 1, number 2, and number 3. And on the surface, we say here that one, number 4. Okay. In number 1 position, velocity is equal to 0. Because velocity is equal to 0, you say kinetic energy is equal to half of mass multiply velocity. And if velocity is equal to 0, this one, it will be 0. Total energy is equal to kinetic energy plus potential energy. If this one is 0, then you will have total energy equal to potential energy. The only thing you have in number 1 position is just potential energy. And this is going to be the max number. Okay. Next thing is in number 2 position. Number 2 velocity is not equal to 0. Okay. What's the number for it? We don't know. So we can calculate the velocity. It's not hard to figure it. We need to know how much time we spend to reach that position. Let's say somewhere here. And next thing is, what's the distance? Okay. So now I can calculate the kinetic energy. The kinetic energy is going to be equal to half of mass multiply square of velocity. And I'm going to call this one here velocity 2. Okay. Velocity 1 was 0. Velocity 2 is not 0. And so we do have a kinetic energy in this case. Let's calculate the potential energy. The potential energy is going to be the total energy minus the kinetic energy. In this case, kinetic energy is not 0. Because it's not 0 and you're subtracting from the total, and the total is constant. Because the total is constant, the potential energy for the second point, point or place is going to be less than the first one. So I'm going to say potential energy for the second position is less than the potential energy of the first position, because EK, or the kinetic energy, is not 0 and you're subtracting from the total. And the third one, right before we hit the surface. In this case, you go with, again, velocity 3 is not equal to 0. So the kinetic energy is going to be half of mass multiply square of velocity. We're talking about third. Velocity is somewhere, let's say, here. Okay. So now the potential energy for the third position is going to be the total minus the kinetic energy. And you want to be more accurate, let's call this one 1, call that one 2, and then we're going to call this one 3. Okay. So in this case, right before we hit the surface, we have the max velocity. So I'm going to say here, V is max. You have the maximum number for velocity. That means you have the maximum potential energy for third position. Let's say here, yeah, kinetic energy is max. Okay. If it's max and you subtract it from the total energy, that means potential energy for the third position is minimum. So if you want to order then the energies till now, you will say the third position, it has the lowest potential energy, and then the second position, then you go with the first position. Okay. How about number 4? Okay. What's going on with number 4? Number 4, position, velocity is equal to 0. So kinetic energy, it will be equal to 0. And also h, or the height, equal to 0. So that means a potential energy that we are looking for it, and we try to calculate through mgh. This one, based on the formula, it will be equal to 0. Okay. So what's happened with the energy? From 1 to 4, what did we do with the energy? Energy must be somewhere. Okay. Yes, based on these two formulas, if you go with velocity, 0, kinetic is going to be 0, h is 0, or height is 0, so potential energy is going to be 0. That's not wrong to say it, but we forgot something, that when we hit the surface and we hear like a bang or like a noise, in reality we are transferring energy to the surface. So now the energy is taken by surface, and by chance maybe the air molecules around it, around this area, around number 4 positions. So energy still is there somewhere, got distributed on the surface, and maybe air molecules around the surface. So it's not correct to say potential energy is 0 and also kinetic energy is equal to 0. Potential energy and the kinetic energy for the object that moved down are 0, but the energy now is taken by other stuff. And we have another version of the potential energy, and we call it the chemical energy. Chemical energy is subject to, we say, composition, or you want to be more accurate, is subject to, okay, so I'm going to say chem energy is subject to position of electrons. And nuclei. Okay. Example, let's go with CH4 versus C2H6. This is methane and this one is ethane. And if you start with 1 gram from each, when you burn 1 gram of ethane, you will see that you will get more energy. Okay, and let's talk about the energy. Where is the energy first, and why we get more energy if we burn ethane? Okay. So here is the molecule of methane. We have 4 bonds of carbon hydrogen versus ethane. Ethane, you will have 6 bonds of carbon hydrogen and 1 new bond of carbon. Where is the source of energy? The energy is here. Energy hidden inside bond between molecules, between atoms, my bad, between atoms. And it depends how far these electrons are from each other, what's the bond length, or what's the bond angle. We call this one bond angle, and this one is bond length. It depends to the bond angle, theta, or the length. Energy can go up or down. This one, it has more atoms involved, so expect to get more energy because you're going to deal with at least 7 bonds. You need to break 7 bonds, and when you're breaking, you're going to spend energy. But when you form a new bond, when you transfer the reactant to products, you might get more bonds, new bonds, and that can be the reason that you get more energy. So the chemical energy is subject to position of electrons and nuclei. It depends how you arrange them. They can be, stable, and they will give you less energy maybe. And the system is so stable, and in order to transfer to product, you need to spend a huge amount of energy. So at the end, you're not going to get energy. Or maybe the compound is so unstable, and when you transfer to the product, it will give you so stable product, and you see heat. So now I'm gonna start focusing on thermodynamic discussion, and I go with something that we call it system. What's a system? System is any object, anything that you are studying to figure its energy. Let's say I have this object. I'm gonna call this one system. Okay, so I'm gonna focus on something tiny, and I try to figure the energy for it, and I'm gonna call it system. Whatever around it, we call it the surrounding. And all, or both this system and surrounding space or area, we call them universe. Okay. So we're talking about system plus surrounding equal to universe. Okay. Total energy, or energy of the universe, is going to be energy of the system plus energy of the surrounding. Okay. And I go with, I keep this one in my mind, that I have a system, it's a tiny area when I compare it with the surrounding, and I'm trying to get energy, or calculate the energy of the system rather than the surrounding, because system is a smaller part. I can focus on it, I can cover it, and I can calculate the energy for it. Surrounding is way higher than the system, is bigger than us, so we do not have control to the surrounding. And if we wanted to calculate how much energy we want to outside, the best way is to calculate, focus on the loss that the system has. Okay. And keep this one in your mind, that the energy of universe is equal to energy of system plus energy of surrounding. Now, I need to introduce two laws, and the first law is going to be law of conservation of energy. This one, it says energy that we are dealing with, we don't destroy it or create. Energy, you can say energy is almost a constant number. You just transfer it from one format to another. So we don't create or destroy energy. Okay, we don't create or destroy energy. Energy, in this case, then, transfer from one format to another. Let's say you have wood and you burn it. You turn the potential energy to kinetic energy. So anytime you are dealing with combustion, you are burning, like let's say a wood, you are transferring the energy that's hidden in that wood or that gas, and you turn it to potential energy, to kinetic energy. Again, example, you take methane and you turn it to CO2 plus H2O. Also, you get heat. Okay, so we burn methane. Methane is a gas. There is potential energy in it, and the energy is sitting inside the molecule. Bonds. When you burn it exposed to O2, you will get CO2 plus H2O, and also you get heat. We use the heat to move our, like vehicles, or maybe to warm places. And again, energy is here. Energy, the potential energy was there. Now you turn it to heat, and heat, it will be taken by molecules, and they start to move faster. We say we transfer the energy to kinetic energy. Okay, this is law of conservation of energy. It's similar to law of conservation of mass. When we were talking about mass, we said if you go with mg plus O2 and you get mg O, you need to balance the reaction. You go with 1 mg, 2 oxygen, 1 mg, 1 oxygen. So we need to have 2 here to balance O. Now you have 2 oxygen, but mg is not balanced, so I will put 1 here. We call this one law of conservation of mass. The law of conservation of energy comes from this one, law of conservation of mass. Because mass is energy. If you say a mass is always constant, then in other words, you're saying that energy is a constant number. And if I transfer mg to mgO, that means I transferred the energy from one format to another format. Second law that we will discuss is the first law of thermodynamics. First law of thermodynamics, it says the total energy of the universe is a constant number. So total energy universe is constant. Okay. And remember, we said energy of universe is equal to energy of system plus energy of the surrounding. The first law of thermodynamics, it says the left part, this one, E of universe, is constant. Okay. And if you are trying to, calculate change with energy of the system or change with energy of outside, you need to keep it in your mind that change with a constant number is going to be equal to 0. Or another way, we remember this one, that first derivative of 4x is 4, but first derivative of 5, which is a constant number, is going to be equal to 0. So if the energy of universe is a constant number, then the change with the energy of universe is going to be equal to 0. And the way you show the change, you put delta. So delta means change. So change with energy of universe is going to be equal to change with energy of system plus change with energy of surrounding. Okay. Left part, because it's a constant number here, this one is a constant number, it will give you delta E of the universe equal to 0. So this one, it will be equal to 0, equal to delta E of system plus delta E of surrounding. Okay, this one is going to help you a lot. So I will put a star on it and I move forward. Go with this, that I got 0 equal to delta E of system plus delta E of surrounding. So that means delta E for the system is going to be equal to minus delta E of surrounding. Okay. Let's go back to system and surrounding shape that we had. So this one was system, and that one was surrounding. Based on this formula, it says whatever we lose or gain for the system is going to be equal to minus change with energy of the surrounding. So if, let's say our system is giving energy or losing energy, then the change with the system, it will be negative. Okay, so we are losing energy. We are losing energy. Change with the energy of the system, it will be negative energy because we lost energy. What will happen with the energy? Energy, it will go outside. It will be taken by surrounding. So I'm going to say change with energy of the surrounding, it will be a positive number. We got energy from where? From the system. So something added to energy of the surrounding, and that's the reason change is going to be a positive, or E2 of the surrounding is going to be bigger than initial energy of the surrounding. Well, E2 of the system is going to be less than E1 of the system. Again, I told you this formula is going to help you a lot to understand the change with energy, change with heat, and later on enthalpy or heat of a reaction. next thing that we're going to go through it is the internal energy. What's the internal energy? Internal energy is equal to kinetic plus potential energy of the system. So internal energy for system, okay, this time I'm talking about just one system, is going to be equal to energy for here the kinetic energy plus potential energy. We say internal energy is a state function. So here energy or internal energy is a state function. I'm going to say energy is a state function. That means we don't care how we transferred E1 to E2. Was it slow? Was it really fast? Was it like in one step or maybe multi steps? We don't care about it. Only thing we want to know initial and final points. And through that one we can calculate the change with energy. And the change with the energy is going to be E2 minus E1. So the state function, whenever you hear a state function, it says energy state function, volume, temperature, or pressure, all are state function. That means we don't care how we got to the final point. We're not worried about that part. Only thing we need to know the final points, the final pressure, final volume, final temperature, minus initial volume, initial temperature, or initial pressure. Okay, and you don't care about the path, the pathway. Imagine, I don't know, we have like a say I want to go here. Okay, and now I'm there. Now I'm here. Okay, I'm here, and I want to go this one. So this one is gonna my first position. You say h1 is equal to 0. Height is equal to 0. I want to go here. This is h2. Let's say h2. My bad. h2 or the height until there is going to be equal to 3 meters. I have two waves, or maybe many ways to get to this position. I can walk and get to this position. Okay. Maybe I can fly. Okay. I can fly and get there, or I can take crane or whatever, one machine, and I will ask them to lift me and drop me there. Bottom line is, when I get there, my height is going to be equal to 3 meters. Okay, so the change with height is going to be h2 minus h1. Change is going to be 3 minus 0 equal to 3. Again, I don't care how I got there. Only thing I care about it, when I got there, my height from the floor now is 3 meters. Initial was 0. So the change with the height is going to be equal to 3. And that's going to be the end of the story for a state function. So energy, later we say enthalpy, temperature, pressure, volume, or state function. So we said we have a system and we have surrounding. Okay, you have to keep it in your mind that your system is going to leak energy to surrounding, or it will get energy from surrounding. It doesn't matter how good you seal your window, always you can see some leakage, or there is a tiny current close to the window. You put your hand close to the window and you feel like a tiny flow, because there is exchange in energy between inside and outside. You think you did your best and you sealed the windows, still there is exchange between them. So we have to write this one, that change with energy of the system is equal to change with energy of outside. And we have a system. System is gonna give heat or maybe energy to outside. Call this one here. Surrounding. Okay. It will give heat, or maybe it will accept heat. That's the reason I showed it by the arrow that is pointing in both directions. So we give the energy to outside as a heat, or maybe we will get heat from outside. Next one, we might do work on outside. So we might do work on outside. So I'm going to say work, or maybe outside is doing work on our system. Example, take gasoline and put it in a car. Treat gasoline as a system. When you put the gasoline in your car, the second you burn the gasoline, it will do work on outside. And outside in this case is going to be the car and the driver. And it start to move the car. So we say the system or gasoline moved the car, did work on outside. System or the gasoline lost some energy to move the car. So we exchange energy between system and surrounding as work. And by the way, when you drive for a while, you can see that the engine of that car start to be hot. That means like while you are transferring the gasoline and to product and use use the energy in it to move the car, you lost some of it as a heat, and the heat it will be taken by the body of that car. And so the efficiency is not going to be like 100%. You did not transfer entire energy of gasoline to work. No, you lost some of it as a heat. What's the point of that one? Is going to be just waste. So we're going to lose some energy as a heat. Okay. Now, if you want to calculate change with energy of the system, you have to keep it in your mind that you might give or get heat from outside. So you need to calculate heat, and also you might do work on outside, or outside will do work on you. So I'm going to say delta E of the system, or change with energy of the system. We can write it as amount of heat that we get or lose, plus work that we do on outside or outside will do on. So we need to know these two. Otherwise, the energy for this system is going to be a constant. If this, if this system is not leaking energy to anywhere, if this one is not leaking energy to anywhere, then delta E of the system, it will be 0. But any system is going to leak energy. and it will link the energy as heat or maybe work. Okay. This one is heat, and unit for it is either joule or kilojoule. Work also must be in joule or kilojoule. So I'm trying to calculate change with energy of the system, and in order to do it, I need to know how much heat we got or lost plus amount of work that was done. And who did the work, system or outside? I go with this, that I have a system. And I have a box around it, and I call this one surrounding. Okay. From now, you need to keep this one in your mind. Okay. You treat yourself as a system, and like you will look to movement of your arms, and you will say, when I move my arm to outside, when I move my arms to outside, I'm losing energy. When they are moving to outside, or you're stretching your arm, you're saying that I'm losing energy. If I'm, moving my arm to my body, in that case, I'm going to say I'm gaining energy. And remember, change with energy, you can write it as heat plus work. So from now, anytime heat is going out, it will have a negative sign. If heat is going out, it will have negative sign. System lost heat. If heat is coming to the system, you move your arm to your body. In that case, we say heat change with here, sign of heat. It will be a positive number. Okay, so first one, heat was negative. In this case, is positive. How about work? Work, I'm going to show it here. If you do work on a system, on anything, an object. If you do work on object, example, this is my calculator. I'm going to treat it as an object. I'm the system. Okay. Again, you treat yourself as a system. I'm the system. I want to lift this. I want to lift this calculator. In order to lift this calculator or this marker, I need to spend some energy. So I'm gonna lose energy. When a system is doing work on the outside, the system is going to lose energy. So when work was done by the system, work, it will be negative. If outside is doing work on the system, work, it will be a positive number. And any one that you pick is energy, whether you're talking about heat or work, energy, because we say energy is equal to Q plus W. So we can write it here. When energy is going out, it will be negative. If energy is coming to the system, energy, it will be positive. So remember this trick. If heat is going out, stretch your arm and point outside. When your arm are pointing outside, heat, it will be negative, work, it will be negative, and energy also will be negative. If you move your arm to your body, then heat, it will be positive, energy positive, and work also positive. So I go with this. If heat is going out, it will be negative. Heat of system, it will be negative. But heat of outside, it will be positive. So when you say, for example, heat went out, how much heat we lost? Let's say we lost minus 15 kilojoule. So what's the heat for surrounding? Is going to be same number, 15 kilojoule, but a positive number. Positive number. If heat is coming to the system, it will be positive. Work. If we do work on outside, if our system is doing work on outside, if I lift this marker, I'm doing work on outside, so I'm gonna lose energy. Let's say by moving this object from here to there, so that this is the first position, I want to put it there. I spend energy to put it there. How much energy I spend? So I'm gonna say the amount of work that system did. This time 10 kilojoule. I spent 10 kilojoule to move it. I lost 10 kilojoule. How much work outside got is going to be plus 10 kilojoule. If outside is doing work on the system, it will be positive. Example, let's say we have a piston. And we are pushing this one down, so that we have a force. This is the volume. I'm going to push it down. This one is going to be the new volume. This is V1 and this is V2. So V1 is bigger than V2. We compress the gas. Okay, this area now is way smaller than the first one. Okay, in order to move it to smaller, space or smaller volume, we had to apply force. We had to apply force to do it, and the force or the energy that we applied now is taken by the gas molecules. And in this case, we see the gas molecule got extra energy. Outside did work on the gas or on the system. Because we did work on the system has higher energy. The second you leave, you lift the or you terminate the external force, you will see the gas molecules will push the piston back, and the volume it will get back to original one. And next thing is the change with the energy. We say if energy is going out, it will be positive, negative. We are losing energy. If energy is coming to the system, then it will be a positive number. But keep this one in your mind. When energy is moving out, it will be negative. So delta E of the system, it will be negative number. And delta E of the system is equal to minus delta E of the surrounding. So you want to calculate what's the sign for delta E of the surrounding. Delta E of the surrounding, it will be minus of a negative number. Minus of minus, it will be a positive number. Okay. You give the negative here, this one it will be negative, and because we know delta E of the system is negative, it will be a positive number for surrounding. Okay, let's practice this formula that we have delta E is equal to Q plus work. We want to calculate change with internal energy. In order to do it, we need to have amount of heat that we exchange plus work that the system did on outside or outside did on the system. So whenever you are talking about thermodynamic stuff, you need to be really sensitive to the wording. How did they phrase that, question? Be sensitive about the stuff like, releasing or giving off. When we say releasing, giving off, or did work on outside, then sign is going to be negative. If it says absorb, got energy, then you're talking about a positive number. Here example. It says we have a system that it says releases. Releases what? Heat. So let's say heat equal to 622 kilojoule. But because it says releasing, sign it will be negative. Okay. Next thing, it says does work on surrounding. Because did work, it will be 105 kilojoule. And again, because our system did work on outside. Okay, our system did work on outside. Work, it will be negative. So now delta E, it will be Q plus work minus 622 kilojoule plus minus 105 kilojoule. And delta E, it will be minus 727 kilojoule. That's the way we use, heat and work to calculate the internal energy. Change with the internal energy. Okay. So now I want to kind of slowly switch to heat capacity and discuss this one. What's the meaning of heat capacity? When can we use this formula? And what's the meaning of delta H? Okay. Heat capacity is the energy that we need to give the system. So it's heat, and we know heat is energy. Heat is energy that we need to give the system to a system, okay, to increase the temperature by 1 degree. Okay, it says 1 degree Celsius. It can be 1 Kelvin, and I'm going to tell you why 1 Kelvin or say 1 Fahrenheit. It doesn't matter really. So we want to increase the temperature by 1 degree. Okay. I'm not talking about the mass. And there is something here that we need actually to clarify. Let's say you have this box, and this box is 2 centimeter to 2 centimeter. Next box you have 3 to 3. Heat capacity, C, or heat capacity, is the energy that we need to give to the system to increase the temperature by 1 degree. Let's say I have these 2 on this bench, so I'm gonna say the temperature right now, T1, for both is gonna be equal to the room temperature and is equal to 25 degrees Celsius. I want to heat them to increase the temperature by 1 degree. So I want to increase the temperature to 26. Now the question, which one of this and which one of these is requiring more time to reach 26 degrees Celsius? Answer is going to be the one that is bigger. This one, because it's bigger, costs you more energy, more time to raise the temperature to 26. But the problem is when we use this formula, heat equal to C delta T, there is no place for mass. So where is the mass? How do we include the mass in our calculation? I'm going to say the mass here, let's call it M2, and mass this one M1. M1 is smaller than M2. So I need to include the mass somewhere in my calculation, otherwise something is gonna be wrong. Mass is hidden inside C. C reality, it has mass, it will include mass, and it has also something that we call it CS, and I will talk about it. We call it specific heat capacity. Okay. So Q is equal to C delta T, and C you can write it as heat divided by delta T. Unit for heat, it can be either joule or kilojoule. And this one, you can go with degree Celsius, Kelvin, or Fahrenheit. It doesn't matter, frankly. So let's go with degree Celsius. Okay, so unit of heat capacity is going to be either joule or kilojoule per degree Celsius. Okay. And maybe you notice in my slide that I had this one, it says QP. What's the QP? Heat under constant pressure. So we call this one heat under constant pressure. Heat under constant pressure, we call it delta H. So heat under constant pressure is equal to delta H. Meaning of this, you were trying to figure change with heat when the pressure of the atmosphere, or pressure, when the pressure was constant. Again, we were trying to calculate heat of a system when the pressure was a constant number. How can I keep the pressure constant? The best thing is do it open to the atmosphere. Okay, do the experiment open to the atmosphere, and that one is gonna, is gonna give you pressure a constant number for, at least for the time that you're doing the experiment. Because we assume that, while we are doing the experiment, the pressure of the atmosphere is not going to change dramatically. And that's solid. There is nothing wrong with it. Okay. So I said Q, we can calculate through C delta T. The bad side of this formula, we don't know the mass. We need to have C. Okay. And we need to calculate C every time we change the container. Okay. For example, see these two, marker. This one, it says, okay, Sharpie, and that one also says Sharpie. Okay. I do one experiment, and I use this Sharpie to do the experiment. The second marker is made by the same company, but there is no guarantee that the mass of the second marker is going to be exactly equal to the first one. Okay, so this one, the purple one, there's no really guarantee that it's going to have the same mass as the green one. So if I wanna use this one, or if I run out of the green and now I have to use this one to do the experiment, I need to recalculate C for it, and that's painful. Okay, we don't want to recalculate C anytime we switch to new container. Or simple thing, you were you were working inside the lab, you had a beaker, and you calculate C, you are half of the experiment, And let's say while you are washing the beaker, like you hit the beaker to one side of, let's say, or somewhere on the bench, and you broke tiny piece of the, tiny piece from the beaker. Because the mass now is a different number, you cannot use that beaker to continue the experiment, because the mass now is different. And because it's different, you have to go back, use new beaker. But there is a problem here. Because your beaker, it might have different mass, you need to start the experiment from the beginning, and you need to calculate C for it. And as I said, this is painful. In order to fix it, we go with this. We break C to mass multiply specific heat capacity. What's the specific heat capacity? Specific heat capacity is the heat that we need to apply, heat that we need to apply to increase temperature of 1 gram from a system, 1 gram from a system by 1 degree Celsius. So this time I'm talking about mass, okay? Heat capacity, specific heat capacity. Specific heat capacity is the amount of energy or heat, okay? Energy or heat that we need to give 1 gram from a system to increase the temperature by 1 degree Celsius. Okay, because we are talking about mass, we call it specific heat capacity. Well, the heat capacity, it was saying the energy that we need to apply to increase temperature of the system. So we increase temperature of the system by 1 degree Celsius. It's not saying how much mass. This one is hidden. We don't know it. And we can rewrite this formula, and we will write it as here. We say QP equal to MCS multiply delta T. MCS multiply delta T. So you will have two formulas, number 1, and this is gonna be the second one. Okay. Where and how I should use 1 and 2. So first formula, number 1, it says heat under constant pressure is equal to C delta T. You will use this formula when you don't have any idea about the mass. So we do not have the mass. Okay, we don't know the total mass. Next one is 2 equal here. QP equal to MCS multiply delta T. In this case, M is going to be the total mass. Okay, you will use this formula, second one, whenever you have the total mass. You know the mass of the beaker, you know the mass of the solution. In case if you put a stir bar and you're mixing that solution, you do have the mass of also the stir bar. So you will use the second formula whenever you have the mass, and this time you are going to use a specific heat capacity. Okay, and keep it in your mind that C is Q over delta T. So the unit for it is going to be either joule or kilojoule per degree Celsius. While in this case, CS is going to be Q over M delta T. So it will be joule or kilojoule divided by gram multiply degree Celsius. This is the difference between C or heat capacity and specific heat capacity. Both of them have joule or kilojoule for the numerator, but the difference is going to be the denominator. The one that it has gram inside the denominator, that's the specific heat capacity. They might not tell you that this number is the specific heat capacity. For example, let's say we have 1.3 joule over degree Celsius versus 2.6 joule over gram to degree Celsius. And they say sign the heat capacity and the specific heat capacity. The one that it has a gram inside the denominator, it will be specific heat capacity. So I looked at the gram. And this one, because it's joule over degree Celsius, it will be just C. Okay. So without telling me name of this number, I can guess which one is a specific heat capacity, which one is a heat capacity. I'm gonna use this formula and show you how to calculate heat. Here's a question that we have. It says how much heat is taken. And so how much heat is taken by a penny that it has initial temperature of, so you go with T1 equal to minus 8 degrees Celsius, and T2 is equal to 37.0 degrees Celsius. Next, mass of this penny is equal to 3.10 gram, and the specific heat capacity is equal to 0.385. Unit is joule over gram to degree Celsius. Now I have two formulas. QP equal to C delta T versus QP CS delta T. Which one do I need to use in this case? I looked at the question and I will ask myself, do I have idea about the mass of the system or mass of the object that we are talking about? Yes, mass is given. Because mass is given, I go with this. So the second formula, it will be the right formula that you need to use. And we go with this. Q is equal to MCS delta T. Delta T is T2 minus T1. Final temperature 37 minus of minus 8, and unit degree Celsius. So delta T it will be 45 degrees Celsius. So now I go QP equal to mass 3.10 gram multiply specific heat capacity, which is equal to 0.385 joule over gram multiply joule over gram to degree Celsius multiply delta T, which is 45.0 degrees Celsius. You cross gram by gram, C by C, and the only unit you will have at the end is joule. The 0.10 multiply 0.385, and that's it will give us QP. Sorry about this one. Okay, QP is equal to 53.7. And the unit is joule. Okay, so I managed to calculate how much heat was taken by the penny. So we had a cold penny. We put the penny in our hand and we hold it until we increase the temperature of the penny to our body temperature. And if we assume that our, like the temperature for our body is 37, a change with the temperature is going to be 45 degree. We know the mass of the penny, we know the change with the temperature, so now we should be able to calculate the heat was taken by the penny. Heat that is taken by the penny is equal to 53.7, and the sign for it is positive. Because it's positive, so we say the penny got or absorbed, okay, got or absorbed energy or heat. So I'm gonna stop here, and this is gonna be the introduction of the thermochemistry. I already made lectures for other parts, and I will share them with you on YouTube, and I also put the link on campus. Have a good time, guys.